The lights are brighter than I thought. Hey everybody, thank you for joining me here in today's session. This is Advanced Shell Scripting for the Cloud. The doors are locked, hopefully you're in the right room. No, just kidding. So this is SVS401-R1, technically, optimizing your serverless applications. My name is Chris Munns. I lead developer advocacy for serverless here at AWS. So myself and my team are part of the overall product organization for Lambda and API Gateway, Step Functions, Event Bridge, SQS, SNS, SAM, and a couple other bits and pieces that are part of this, this wonderful world that we call serverless at AWS. So why are we here today? So again, we're talking about serverless applications. We're going to be focusing primarily talking about Lambda. I'm going to hope here that most of you in this room have a bit of information and knowledge about Lambda, though I know there are some folks that this week is probably the first that you're hearing about it. Since this is a 400-level talk, though, I'm only going to be skimming over some of the basics. And I've got a whole lot of things to talk about here in the next hour. Can you all start the clock for me, please? In the next hour here before we let you out of this room. So let's dive into this. Again, we're going to be focused talking about Lambda. For those who don't know, Lambda is what we consider a serverless compute offering here at AWS. What makes it serverless is that it meets four different criteria. So the first is that there is no infrastructure for you to manage. This means no physical, no virtual, no container orchestration that you yourself have to take care of. The second is that it can scale with usage. So as requests come in, it'll automatically scale up, scale down, and you shouldn't really have to think about managing that yourself. Although I'll caveat how that changed a little bit this week. The third is what we call pay for value. And typically for things like Lambda and API Gateway, this means paying just for what you use. But as we'll talk about some of the new stuff that came out this week, it also means paying for getting the performance that you need out of your functions. And then finally, high availability and security being built in. At AWS, we always talk about security being our #1 priority. And throughout Lambda and many of these products, security is deeply ingrained in a number of different ways into the products. Now, this is a talk about optimizing serverless applications, and it's important to understand kind of what makes up the application in this case. Now, when we talk about an individual Lambda function, it basically has kind of a stack of things that are below it. So at the bottom tier is the actual compute substrate, or the underlying, I would say, physical infrastructure up through the hypervisor that is running the infrastructure above it. On top of that, then we have the Lambda service itself. So this is things like the APIs that you interface with. This is all of the management layers and worker tiers and stuff that we then operate that execute your code on behalf of your application. We then have the actual execution environment. So this is the actual thing that's running on, in this case now, the Firecracker micro VM hypervisor that your then runtime, so the language that you pick, and then your function code runs inside of. Now, across these 5 different parts of the Lambda function, there are only a couple where we can expose knobs and levers up to you. And so we're going to be primarily focusing on just 3 of these parts here today. The function itself, so the code that you write, how you build it. The execution environment, so how you configure your function, the infrastructure around it, events and stuff like that. And then finally, the thing that we announced on Tuesday, which is how you can actually tweak the underlying Lambda service now to get better performance for your functions. And so again, we're going to work our way through these 3 levels. So let's start with your function. So again, the way that Lambda works is we run a massive amount of compute infrastructure at AWS for Lambda. When a request comes into your application that's powered by Lambda, it's going to go into an event source. That event source is going to trigger a Lambda function. And that Lambda function today can be written in one of 6 languages that we manage for you. So the 6 that you see listed here: Node.js, Python, Java, Go, .NET, and Ruby. Or you could be using the Runtime API, which we announced last year at reInvent, which allows you to bring pretty much any language you can think of to Lambda. So we have customers doing using languages like PHP or Swift, other JVM-based languages, and so there's a lot of options that you could have with that. Now, in terms of the anatomy of a Lambda function, there's a basic concepts I want everyone to know. The first is the handler. This is essentially the part of the function that contains your business logic, where when we go to pass an event into, we're going to execute the handler part of your code. What we pass into that handler then when an event comes in is first the event context, or event object, I should say. So the event object is the JSON structure that contains the information about whatever it is that's happening that you want to respond to. So in the case of an API-driven request, it's going to have all the bits and pieces of information about that API call, the client, where it came from, what the call is, any body or parameters that are passed in. And for example, with a invocation that was caused by Amazon S3, it'd be things like the bucket, where the key for the object is, and so forth. We then also have the context object, and the context object is a little bit different as this is something that is more related to the underlying platform itself, its configuration, things like timeout, memory settings, and stuff like that. And so you might have code in your application that interfaces with the context object, pulls that information with it, or deals with it according to various needs. Now again, you've got an event source. We have well over 100 different services today at AWS that can either directly invoke Lambda or that you would use to invoke Lambda via, say, Amazon SNS or Amazon EventBridge or another similar service. And these represent everything, again, from things like calls to API gateway, to calling Alexa, to changes in data state, so responding to records or items being modified inside of a DynamoDB database, down through things like management events in your infrastructure. And so we see Lambda being used really as a kind of for all sorts of different use cases, but especially as a glue for things like infrastructure events and stuff like that. So if we build off that handler, and again, this is kind of some pseudocode here. We have our handler, and then one of the other capabilities that we give you in Lambda is the ability to run code before that handler executes. So we give the ability to essentially initialize pre-handler aspects of your code base. Now, customers use this to do all sorts of things. You might be including third-party packages or dependencies, whether they be open source or ones that are created inside of your business or that you've created yourself. You might be establishing variables that represent certain aspects of your application. You might be calling other functions, talking out to other services, connecting to databases, and so forth. And so this area where we have things, again, like dependencies, configuration information, and common helper functions is kind of the second area that we see your code base expand into. Now, there are some best practices for this. So a couple of these I think should be pretty straightforward. One, only import what you need. In a situation where, again, Lambda performance is tied very much to the code very directly, importing packages that you don't need, keeping in packages that maybe you used in development but that you don't need in production is all kind of wasteful towards the performance of that function. So where and when possible, you want to slim down SDKs or use fewer SDKs or fewer packages, fewer dependencies, and so forth. The second is that pre-handler code is really great for doing things like establishing database connections or pulling in secrets. And we see a lot of people do that, but you want to be prepared that you might need to then handle that again in the future. And so we do encourage it, but again, you don't want to think that just because you did it in the handler that it will always stay there or that it will always be accurate. So you want to be cautious about how much that stuff can change, how timeouts might impact it, and only kind of appropriately use it in regards to that. Now, there are a couple other aspects about Lambda that make it fairly unique as a compute service. It's basically 100% ephemeral. What does that mean? You have no guarantee that from one invocation to another invocation that you will land on the same compute resource. At scale, it's practically impossible that you could have any sort of assurance that you would do that. But even at a very low invocation rate, there's no way that you can guarantee that we haven't decided to spin up another resource for that on your behalf. So things you want to be aware of. One, lazy load variables that you don't need all the time in your code. If you have any sort of, say, forked logic inside of your code where 80% of the time it's going to go down path A and 20% of the time it's going to go down path B, maybe only initialize the stuff that you're probably going to need for path A, and then when you execute in path B, then initialize, import, include, etc. Again, if you don't need it, don't load it. All of that init stuff that you do pre-handler impacts cold starts. And so from the point in time where when we get an event for your function, and then what we have to do is say, is there a compute resource that is A, aligned with your account, B, that has your code on it, and then C, that is warm and available to take an invocation, and then to be able to, if we don't have that, find one, download your code, again, align it with your account. We then have to bootstrap that environment. And so all of the stuff that you do pre-handler can potentially slow that down. And then finally, one thing that even though these environments are ephemeral, they do get reused. So in between invocations, we effectively freeze the environment. On a subsequent invocation, we thaw it back out and use it again. Depending on the programming language that you use and the type of constructs that you use inside of it, there could be resources that you establish, there could be variables that you set, there could be handles or connections that you make that use sockets that would get reused. Literally just today, I got an email from one of the technical account managers here at AWS. They have a customer that's running into the open file handler limit that we have built into Lambda, which is 1024. And what the customer is doing is they're taking in records from Kinesis. They're then contacting or making an HTTP call for every one of those records. And the function basically is not closing those connections at the end, so they run into resource starvation. So again, that's the kind of thing that can happen if you aren't being careful about what types of reuse you do try to use in your function lifecycle. So again, this covers some of the pre-handler stuff, what you can do. But also there are, again, these places where you might have certain actions you want to take inside of your code. So this could be doing things like grabbing configuration information, connecting to databases, reading configuration files, and things like that. So I'd consider this to be common helper functions that might exist inside of your code. Now, when it comes to configuration information, we've got basically two main models for how you might want to get this into your code. And no, putting it hard-coded in your code is not one of those two options. But the first is with Lambda environment variables. So Lambda environment variables built into the product. What these allow you to do is basically expose a key value pair that is made available at the operating system level of the function. And what this means is that you can just use the standard language-based APIs for reading operating system environment variables. So we see here an example for Node.js where it's process.env. For Python, it's os.environ. I don't know anything about any other programming languages, so I don't know what you do with those, but I'm sure it's pretty straightforward. It was a joke? It was a joke. Someone laughed. I got a ha-ha to like someone all the way up there. No, so again, it's really easy and straightforward to pull these in. Now, these key value pairs can be used for things like configuration parameters, feature flags, potentially passing in secrets, so things like usernames, passwords, API credentials, and so forth. Now, we give you the option to optionally encrypt these yourself with KMS. So KMS, the key management service, gives the ability to manage the keys and handle rotation of them and all of that. Now, one downside to this model is that you then have to give your function access to those keys, and you also have to spend at some point time grabbing the encrypted payload and then decrypting it into the information that you need. Now, typically, people will do this in pre-handler code. But again, if you ever have a situation where those values might change, you'll have to come up with some sort of out-of-band mechanism to basically flush out all your Lambda functions. That typically means making some sort of a change to the configuration of it. But again, these can be really useful for doing things like creating multiple environments, for providing dynamicness to your functions. One other downside to these is that they are only local to a single function. So if you have, say, an API-based workload and you've got 30 functions in that workload, each of the environment variables could be uniquely configured for them, but again, they're not made shared across all of those functions unless you're using a deployment tool or something to do that. So if you need a more centralized option for storing this type of information and distributing it, we basically have two other services that can be really useful for this. So the first is AWS Systems Manager Parameter Store, and then the second is its close cousin Secrets Manager. So Parameter Store, as the product name might allude to, allows you to store parameters. Again, it's key value pairs that can be made available to your application. These are stored in a hierarchical structure, which is actually really awesome. I find this to be really, really useful. You could have hierarchies, say, per application, and then per environment, and then per application, per business units, all sorts of different ways that you can separate out the various environment variables that you might need for your application. As you can see here, there's a bunch of other good benefits to it: CloudTrail logging, notification of changes. Again, these can be encrypted with KMS, so there's a lot of different things that you can do here. And you can also be really fine-grained with IAM policies about which function can access which data inside a parameter store. Now, Secrets Manager works very similarly. It allows you to store key value pair information, allows you to encrypt it. There are some added benefits to Secrets Manager in that it is integrated with a number of our database services, including RDS. And so, and as well as the fact that Secrets Manager supports the ability for you to do rotation of credentials. So this can be really valuable for you if your organization has, say, a password rotation policy or retention policy, that you can automate this process with Secrets Manager, have it directly integrated in with your application, never need to put hard-coded credentials anywhere. One awesome thing that the Parameter Store team did is now over a year ago, but that most people don't know, is that you can actually use the Parameter Store API and SDK calls to also pull information from Secrets Manager. So from the single client that I added to my code here, to the get parameters calls that I make here as well, it's really easy for me to also pull in information from Secrets Manager. So I could store non-secret configuration or feature flag information in Parameter Store, store secrets in Secrets Manager, and just have to make basically one client's SDK calls to get them out. Again, these parameters and these secrets can be shared across Lambda, across containers, across EC2, across things that live outside of AWS. It's a public API that you can pull. And so this could be a really flexible way for sharing information across a larger organization, whether serverless or not. Now, another thing that often, or the third kind of aspect to our Lambda functions that we have here is what we end up doing with them, right? So Lambda functions execute your business logic, whether it's talking to databases, data stores, other APIs that might exist inside AWS or of your own. And so it's also pretty common then for you to use common helper functions to connect to those resources, to establish new connections, to connect to databases and things like that. The final thing that you'll typically see inside of a Lambda function is going to be your business logic. So as a recommendation, we encourage you to separate out your business logic from the handler. This allows you to, as we'll see here in a moment, be able to take this code, reuse it in other places, and share it. And so the fourth part here, again, that we have to our Lambda function is the business logic subfunctions. Now, again, regardless of your programming language, these are kind of the main top kind of common 4 types of code that we see in Lambda functions, and there are various mechanisms and things about how you want to think about them. Now let's assume, though, that I have an API-based workload. So I have an API gateway, I have a number of API functions. I'm following the practice where I map a single API function to a single Lambda function, and then each of those Lambda functions needs to talk to my database, my secrets manager, my parameter store, what have you. You end up with a diagram that starts to look something like this, where again, I have individual routes mapped back to individual functions map back to the resources that they need. Now, inside of here, we could have a lot of duplicated code, right? Again, if we go back to this, we think of all 4 of those areas repeated. Now, our handler might be unique, some of our business logic might be unique, but more often than not, our pre-handler code, our helper functions, the things we import is common across all of these. So what can we do to reduce this? Last year, we launched a capability called Lambda Layers. And so Lambda Layers basically helps you directly solve this problem. It's a very common one. And what you can do with Lambda Layers is you can bundle up all of this shared code. You can bundle up all of this stuff that's not business logic, that's not your individual handlers, and then make it available to all of your functions. Now, there's a number of pretty cool aspects to layers. They are immutable. So when you create them, they basically are frozen in time. And then when you update them, it creates a new version ID for them. And so this means that you can rely on them to be basically static throughout the lifecycle of your functions as you update them and change them. Layers are part of the same maximum file size limit that we have for your application artifact. So that today is currently 250 megabytes uncompressed. So you do want to be aware about how much data you're putting into a layer. But again, this will reduce typically your main code artifact size by shifting things over to the layer. Now, again, with layers, they are just another zip file that you upload to the platform and create as a named resource that you then configure back to your function. You can create today up to 5 of these. This is a hard limit. This is something that we're trying to basically keep people following certain good practices. We wouldn't want you to have a Lambda layer per package dependency. We'd rather see you collect all those dependencies up into a single layer and then attach that. Now, layers, when you connect them to a function, again, you can have up to 5 of these, we basically squash them down. At the end of the day, it's considered an onion file system behind the scenes. So what this means is if one layer you have /foo, another layer you have /bar, in the same file structure, you're going to have /foo and /bar. Now, this can be really useful if, for example, you have, say, a layer that contains a lot of common dependencies and packages, and you need to update one file inside of it. You could add another layer with just that file, and basically we'll squash down that one file onto the other layer and overwrite it for you. So it becomes a really nice way to kind of cherry pick patches or updates to certain things that might be shared inside of a layer. So again, with Lambda layers, we then basically get to take some number of these 4 areas, strip them out, put them in a layer, make that become shared that way. There's no performance penalty for this. There's no real performance improvement to this. Completely unnoticeable to your Lambda function. But again, from a development perspective, it helps make life a little bit easier. And so we end up with, again, a diagram that starts to look more like this. Now, one thing in this diagram is I have chosen DynamoDB. And I would say that for us here in the serverless world, we have favored DynamoDB and non-relational databases for quite some time. We often hear from customers, well, what do I do about relational databases? How do I handle connecting to them, reconnecting to them? How does this whole life cycle of a function matter to that? And so this has been traditionally a challenge for customers trying to deal with that. So on Tuesday, we actually announced a new service, or co-announced, I should say, with RDS, a new service called RDS Proxy. So RDS Proxy, much like the name sounds, is a proxy service for relational databases. It's currently just in preview, and it supports RDS MySQL and Aurora MySQL. But you can foresee a future where it will support more things. And so what this allows you to do is basically have your Lambda function connect to the proxy then connects to the database. It integrates with Secrets Manager, so you don't have to worry about doing any sort of secrets management back to your function anymore. You could also just use IAM authentication to the proxy. The proxy, again, is much, much more efficient. So very often we heard from customers that they had to oversize their RDS instance to deal with the scale and fluctuations of Lambda. that all goes away. If anything, you'll see many, many fewer connections due to the proxy. It also can help handle for you things like the HA failover behind the scenes of the RDS instance and making things more efficient in terms of that. So a bunch of new capabilities here with RDS proxy. We think this is pretty cool. Do any of you think this is a pretty cool thing? A couple of you? Awesome. Encourage you to check it out. Again, just in preview, but should move pretty fast into GA here, we're hoping. Okay, next thing I want to talk about is a pretty straightforward concept of less code being greater than more code. And when we talk about this in terms of Lambda and serverless, we always come back to less is more, less is more. So when it comes to talking about Lambda functions, there are a number of ways that you can write less code. Now, one key thing that my manager, who is the director of product development for Lambda, JNAR, always talks about is that you should use Lambda functions to transform, not transport. What does this mean? There's a lot of situations where you might be getting data from a certain service coming in, say via maybe S3 or via, say, Kinesis, or even just through an API, and you're just going to take that data and move it someplace else. You're going to move it to a database. Maybe you're taking data from an API, you're going to put it in S3, or collecting data from Kinesis, you're going to put it in S3 or Elasticsearch or Dynamo. These are all really poor use cases of Lambda unless you're actually going to transform that data, so do some sort of modification of it. We have a whole bunch of purpose-built services at AWS now that do this a lot better for you. So we have things like Kinesis Firehose, which could take data in, automatically put it into places like S3 and some database services. We have services like Glue, which can do ETL workflows for you, so you don't have to try to do that type of a thing inside of your functions. We have services like Batch that can do batch processing, so on and so forth. So wherever possible, you want to try to avoid that concept of just doing real basic kind of dummy shipping of data between two places. Another good example of this is that with API gateways, REST APIs, you can actually connect API gateway directly to a number of AWS services, like DynamoDB. So instead of building a really basic kind of CRUD interface shim in Lambda between DynamoDB and API gateway, you can actually plug API gateway directly into Dynamo and expose that out to applications. And so that can be really powerful as well. Now, another thing which we'll talk about here is that you want to try to leave retry and failure handling to the service. And in this case, we'll talk about some new capabilities that we have here, but it's getting away from putting a lot of this code into your function. And then finally, from inside your function, you want to avoid as much as possible doing reduction of data inside of your function itself. Now, this doesn't mean when the event itself comes to the function, but if your function is going and reading from a database or a data store, you want to try to avoid as much as possible reading in a whole lot of information and then filtering that down, because that ends up just being costly and kind of not efficient. So you want to use mechanisms like fine-grained queries and databases, or things like S3 Select, or in the situation where you're getting in events from places like SNS or EventBridge, making sure that they're worthwhile to you. And again, it's just making sure that you're doing less inside your functions. Now, another thing that we often find is that business workflows are rarely just a straight line. You very rarely are just going from point A to point B. You typically have to do some sort of maybe decision tree logic, some sort of failure handling, some sort of retry logic, potentially an exponential backoff and retry. And so this is where we typically recommend that customers look at services like AWS Step Functions. So now with Step Functions, what you're able to do is take all of that business workflow logic, all of that after A, depending on the result, do B or C, or maybe do A, B, and C together and combine the results, or maybe if B fails, I want to go down a certain path. So all the various decision tree logic that you would have inside of an application, you could bring up to a service like Step Functions. Now, just yesterday, we announced a capability called Express Workflows and Step Functions, which actually makes Step Functions way faster, way more lightweight, and at a way lower cost. And so with Express Workflows, what you can do is inside of, again, very quick, discrete, there's a 5-minute maximum limit on a job compared to a year of regular Step Functions work. And so Express Step Functions, we think Express Workflows for Step Functions, we think is going to really change the way that you think about some of this logic yourself. Now, Step Functions, when it first launched with Lambda as its main integration point. And again, the idea here was to allow for all the capabilities that you see up here, plus some others, to make life easier. But beyond that now, Step Functions has a whole lot of integrations directly with a whole bunch of other AWS services. So we have integration with things like SQS and SNS, with ECS and Fargate, with SageMaker, with Batch, with Glue. And then just about 2 weeks ago, the team announced integration with EMR. What this integration means is directly from Step Functions, you can talk to these services. So instead of you taking data from, say, one service and passing it to another, again, transporting it yourself, you can have step functions take this and do it on your behalf. As a brief example of this, if we were going to be managing, say, a batch workflow, and we needed to kick off the batch workflow, we needed to check for it to be done, and then depending on the outcome of it, either message that there was a success or failure. If we were just doing this with Lambda and we were using step functions to manage that workflow, you would see the diagram that you see on the left here, where we've got about 8 different boxes of logic that we'd have to think about. Whereas if you look at the diagram on the right, where we've integrated step functions where it's going to call batch, and it's going to figure out what the outcome of that execution in AWS batch is, and then based on the outcome, it's going to use SNS to either send a success or a failure message. We basically have no Lambda functions that we need to write to do this whole workflow. And so that could be really, really beneficial to not even have to bother having a Lambda function. Now, the next thing I'll talk about, kind of in the same kind of vein as this, is a new capability that we announced in the last 2 weeks leading up to reInvent, which is a concept called Lambda destinations. Now, for a number of years here, we've had a concept called DLQs, or dead letter queues, whereas if a Lambda function fails to execute, depending on the retry policy, it could capture the failed event, and you could put it through what's called a redrive of potentially re-executing or looking at that event or figuring out what to do with it. Now, that was really useful, but what we heard from customers, especially for asynchronous-based workflows, is I want to understand actually what the success of my function looks like. So take, for example, a time where you have a customer that uploads data to S3. Maybe they upload an image or a document or something like that, and it kicks off a Lambda function. The Lambda function processes that. Depending on how your workflow for that needed to be done, you may have had to then, say, write a log message, call another API, put a message someplace else. And this was, again, code that you were writing to transport information, not transform information. Now what you can do with destinations is you can say, either for success or failure, pass it on to one of these other destinations that you see listed up here. So from a Lambda function, you could automatically have the success, both request and response, captured by either another Lambda function, SQS, SNS, or event bridge. Now, in a failure situation, a place where this becomes really powerful is we're also now, again, extending beyond DLQs to give you both the request and any response that was generated by the failed function. So imagine, if you will, a situation where your Lambda function times out, where it runs out of memory, or doesn't have enough storage to complete an action. You can basically take that failure message, pass it into event bridge, pass it into SQS or SNS, and have it picked up by a Fargate task, have it picked up by an ECS container. So all of a sudden, the limits that were in Lambda before that might have blocked certain workloads, where you say, hey, 99% of the time it works fine, but 1% of the time I get a request that doesn't. Now you can basically pass this on to another part of your architecture, be able to handle it. So again, that 99% of the time, it'll follow the normal workflow. That 1% of the time, you can capture it and do something different with it. For success, you have the ability to say, okay, I've processed this record, I've processed this event. Now take this message and send it off to, again, event bridge to kick off a step functions workflow or do something like that. So a whole lot of cool stuff that you can do with this. It's going to enable a whole new world of patterns with Lambda and with distributed architectures with it. And so we're pretty excited about this one as well. So I'll leave you with the final comment and thought on this, right? What we feel is really the best performing Lambda function is the one you never have to write. And so again, whether we're talking about step functions, we're talking about some of these other capabilities of event destinations, some of the stuff we'll talk about here in a little bit about some of the async services. These are all things that are going to reduce the code that you have to write. I would love to see you have your applications be 100% Lambda, but have them be very few Lambda functions because you're using these other services. So this kind of summarizes the your function aspect of this. Again, there's a whole lot of different areas that we've had here. I will have a slide at the end of this talk that has all this put together in one place, so don't feel like you have to grab this one just yet. Cool, so let's move on to execution environment. Now, I've already kind of talked a little bit about the lifecycle of a Lambda function. Basically, at the end of the day, we run this pooled compute. When we get an invocation, we have to find a compute resource configured for your function that has your code on it. If we don't have that, we have to make that happen. And that's basically everything that you see that's in the red box that says full cold start here. Now, if we have an execution environment for you that's been used recently, it's considered a warmed or semi-cold function execution. We might just have to bootstrap the environment or just execute your code. So you can see here kind of this dividing line between places where we have our optimization and the places where you can do your optimization. Now, a lot of the places where you can do your optimization is a lot of the stuff that we just talked about in the previous section, talking about keeping your pre-handler code low, making sure that the code that you're executing is purposeful and valuable. Those are all good things. But there are a couple areas that you can still tweak and tune here. So one thing I'll say, though, is that in terms of understanding the impact of this, you can't understand performance improvement without measuring performance. And so X-Ray, or AWS X-Ray, is a service that's deeply ingrained in Lambda and API Gateway and a number of other serverless services. And this gives you a really easy ability to be able to view performance of your functions. You can turn it on, turn it off as need. And so you can capture data in dev. You can capture a percentage of data in prod. You don't have to run it 24/7. And so that can be valuable to you as well. Now you see here that it gives you this pretty nice little map. It's got circles and colors, and that's a lot of fun. But you could dive into those circles and find out a lot more information about what's happening inside of your architecture. Now, on an individual function basis, we also get the ability to see this waterfall diagram of what's happened inside of your function. I got asked earlier this week this question, how can I capture even more data? So the X-Ray SDK, which I have kind of shown up in the code sample up above here, also gives you the ability to create what are called custom segments or custom annotations. And it's basically just a single line wrapper in front and then a single line at the end to capture a block of code. And so you have the ability to generate information that is unique to your code base that would show up then here in this waterfall diagram. The X-Ray team also just announced something last week, which is called trace maps. And basically what it does is it allows you to trace a single request through a distributed system, being able to draw a map that looks like the one that you see here. Now, originally, this map was an aggregate of all of the traces that were collected. But now with trace maps, you can take a single single execution, track it through Lambda, through other services that are integrated with X-Ray, and get a whole lot more information. So that's a new capability that's in X-Ray now. Now, when it comes to performance with Lambda, literally up until Tuesday, we gave you one knob. And that was the amount of memory that your Lambda function is configured for. Now, as you turn that knob from 128 megabytes up higher, we give you a proportional amount more CPU and network. Now, sometimes people get kind of confused about this. Why not give us a knob that gives us CPU power? The challenge is that giving people, say, a gigahertz rating or telling them that they have X number of CPU cycles is a really, really abstract, hard idea. It's hard to measure. But if we tell you that you have a certain amount of memory and you turn this knob and you get more CPU, it's a lot easier to kind of conceptualize that. So again, as I go from 128 to 256, I effectively double the CPU power that I have, or the CPU capability of my function. As I go from 256 to 512, the same thing. And so again, as you turn this up, you'll find that your functions will potentially, or most likely, behave better than when it's lower. Now, I talk about this being really powerful for things that are CPU bound. And often I find that people are sometimes unsure of what it means to be CPU bound. Just as a really kind of straightforward example here, across the industry over the last couple of years, people have been moving from SSL certificates that were 124 bits up to 2048. That move from 1024 to 2048 didn't just cause a doubling of what a CPU needs to do. It's actually a logarithmic jump in the amount of CPU power that it needs in order for you to be able to do SSL handshaking and communication with a 2048-bit cert over a 1024-bit cert. So if your function is talking to a lot of HTTP-based services, you will find almost immediately that by turning up this knob and giving your function more CPU, even if you're not using more memory, will be beneficial to you. But let's actually see an example of this. So I have an example here, which is the most basic kind of example possible. We're going to take a function. We're going to calculate inside of it 1,000 times all prime numbers that are less than 10 million. This is a very kind of basic CPU-heavy example. And what we can see here for 4 different memory configurations is as we go from 128 all the way up to 124, we do get a considerable performance improvement. But if you look at the cost aspect of this, you see some very light fluctuations, but it can be a little bit harder to pull apart where the best value is. But if we were to compare the 128 numbers with the 1024 numbers, what we find is that we basically shave off about 10.25 seconds. So roughly 90+% of the function duration between 128 and 1024. And it only costs us 0.0001 of a dollar more per invocation. And so you have to ask yourself, does that 0.00001 more worth it for you to shave off 10 seconds on your function? And so again, this is the type of thing that you might see with as you turn up the memory knob, your functions get faster, and they can also then become cheaper over time. Pardon me. Awesome. So again, with this knob that you turn as you go from 128 up to the max of 3 gigabytes, we give you more CPU power. Now there is basically a top-off point for a single core, which is at 1.8 gigabytes. We then give you a second CPU core. Now, most people's Lambda functions are not multi-core or multi-thread friendly by default. So going above 1.8 is actually not going to do anything for you, unless you're I/O bound. So unless you're pulling a lot of data in through that network interface, it's otherwise not going to do a whole lot for you. So again, I would say encourage you to test your functions just up to 1.8 gigabytes, and that's probably, again, where you'll see that top out of that CPU benefit. Now, another area where we've seen performance be a concern in the past was when connecting a Lambda function to a VPC. So back in September, we announced that we were rolling out a brand new model for how VPC networking and Lambda functions works. It works by basically shifting the way that we create an elastic network interface inside of your VPC for the Lambda functions. It uses a technology at AWS that we have called Hyperplane to create what's called a VPC to VPC NAT. Much, much, much more efficient, much, much less use of network resources, and much, much faster, as you see here from the brief kind of example that we have. So we took a function, we executed it without this. It took, again, over 14 seconds for it to complete its execution. We then put it in this new environment where we have this VPC to VPC NAT, and it took less than a second. In general, what we find is the cold start inside of a VPC now is well under 1 second, typically under 500 milliseconds. And so this is a massive, massive improvement to how VPC networking with Lambda used to be. We're also happy to say that as of last week, this is now available in all of the public regions globally. So if you have Lambda functions that are connected to a VPC today or over the last couple months, you've actually seen this improvement roll out. You may not even know about it. It was completely kind of silent behind the scenes per account. But this is out there now globally for everybody. So this is pretty cool. Awesome, so I want to talk a little bit about events and how events matter in terms of how you think about building your functions. Now, one of the other things that's very unique to Lambda is that there's no ability for you to connect to it over a port or a socket. And that's something we're all very traditionally used to doing with, traditional compute environments. You can only basically get a Lambda function to do a thing over its API. Now, this is similar to almost every other service that we have here at AWS, that there is an API, but again, it's different in the sense that it's the only way to access the compute resource. So with Lambda's API, this is built into all of our SDKs, our CLIs, all of our tools. All the services that invoke Lambda on your behalf, like API Gateway or S3, are doing that via the API that we provide for you. You also have the ability to take the SDK and create your own client, so you could use this inside of your own code and call it either synchronously or asynchronously. Now, those are the two main models that we support with the SDK. Again, a synchronous model, so an example of, say, an API, we call a route. API Gateway invokes our Lambda function. We expect a response back up to that API Gateway. In the asynchronous model with things like SNS and S3, where it's going to take either a message or an object, pass that on to our Lambda function, there's no route or path back up to S3 or back to SNS. And again, this is where the new event destinations capability helps you out with that type of workflow. And the third option that you have is what's called a stream-based model. And it's actually a bit of a combination of the asynchronous model and a bit of a different way of interfacing with things. So with the stream-based models for Kinesis, for DynamoDB streams, and for SQS, we actually run a puller on your behalf that pulls messages and records out of those services and then creates a Lambda invocation directly to your function code. Now, that puller is completely controlled by us. We give you some knobs and levers. But again, what this allows you to do then is to easily integrate with those capabilities. Just 2 weeks ago, we announced SQS FIFO support, so first in, first out queue support directly with Lambda, which was one of the most heavily requested capabilities in terms of these asynchronous event sources. And that should actually say stream-based. Now, one thing that we find with customers building applications with serverless is that there's a heavy, heavy reliance on synchronous workflows. And we also find then is that people have a lot of trouble with synchronous workflows. So what goes wrong? Well, we all get the basic idea of if we had a single service out there, and we have a client, it talks to our backend, synchronous application, it's going to respond and say, okay, I did the thing. Now, if there's a failure situation, typically what we would have is our client, a browser, a mobile app, what have you, go back and retry that execution if it was something that could be retried. And so this is a really easy failure model. The client that we create, our browser, web app, et cetera, could just make another request, and there it goes. Now, as we start talking about distributed applications, you find that the complexity grows much more than linearly. So if we have our first service talk to a second service, what we find is we haven't just added one more failure path, we've actually added several. And so when we have to think about how we recover from this, it starts to, again, you have to ask a lot more questions. Basically, who owns what retry? Who has to report it? What does the client see? What is their expectation? And across these various failure scenarios, that all becomes a point of complexity. And so, again, as customers are building more and more of these distributed systems, the synchronous model starts to become a point where you end up writing more code, right? We want you to write less code. We want you to do more intelligent things with your applications. So we think about shifting this to a more asynchronous model, whereas the first service calls the second service, but then replies back up to our client saying, hey, I'm all good here, things are done. Then we all of a sudden don't have that same kind of brittleness to our application. And so in the case of, say, a user-based client, what you can then have is your application, again, your client calls the first service, invokes the second service, but replies back saying that it's done. And then at some point, if your application or the client needs information from that second service, it can just pull it. And I've heard or talked to a lot of customers where they say, no, this breaks our application experience, this will never work. But realistically, this is how some of the biggest sites in the world react. If you look at, for example, if you've ever bought an item off of Amazon.com, we do asynchronous stuff everywhere. When you go and click that buy button at the end of the cart experience on Amazon, we don't immediately say, here you go, here's your gift, it's coming to you right now. We actually take you to a page and say your order has been placed. We'll send you information when it's been updated, we'll send you tracking, et cetera. All that's asynchronous. So there's a lot of places and a lot of use cases where asynchronous can be valuable to you. And so again, if you don't need a response right away, execute async. This is built directly into the Lambda SDK. Now behind the scenes with async, we actually maintain an SQS queue, or queues I should say, that will hold that message, and then we pull that out and inject it into the worker environment. Now this is what we do for async, but it doesn't give you all of the controls and ability to handle things like failure that you might want. And so for that, we would encourage you to look at a service to handle that asynchronous communication. We basically have 4 different main services that can do this for you today. We have SNS, we have SQS, Event Bridge, and then Kinesis data streams. Now, if we're all the way here towards the end of day 4, so hopefully you've had a chance to attend one of the other sessions talking about asynchronous applications or distributed workflows. If not, there were actually a lot of great talks this week that you could find the videos and slides on next week. And when we talk about these 4 services and we think about what fits, there's actually a number of different ways that we can compare them. And again, this is a huge topic that we could spend a half a day going into depth about how you think about these. But I find that these 6 kind of key factors are really the things that you want to think about for each of these. And again, the differences between SNS, SQS, Kinesis, and Event Bridge for each of these can be minimal for some, but then more drastic for others. I'll take just one of these for example, which is concurrency. Now with concurrency models across the SNS model, the queue-based model, and the stream-based model, concurrency is not just take an item out the other side of the hose. With SNS it is. We're able to pull that data off of that SNS topic or get it as fast as SNS can send it to our Lambda function. And what that means is that SNS can do very, very, very rapid, fast throughput. With SQS, both with standard and FIFO queues, we grab objects off in batches from the queue. And so that means that your Lambda function gets a batch, and then it can do whatever it needs to do with that. With Kinesis, though, we have 2 mechanisms. We have the number of shards that you have inside of a stream, and then we have the batch count that you pull off from that. So you're actually executing many more events in parallel, ordered based on the shards that you have inside of a stream. So again, each of these involves a different amount of throughput, different amount of events that can be processed over a period of time, and a different amount of durability and duration that the objects or events might live inside of these services. So again, just one way to think about it, that depending on your application, you might need one of these more than the other. Now this is a rapidly moving space for us here as well. We announced a whole bunch of new capabilities for both stream and async models in the last 2 weeks. You might have missed some of this, so what we did is actually right before reInvent, we put up a blog post on the Compute blog, which we called the pre-event post. This QR code takes it takes you directly to it, but if you don't want to take a picture of this, you could just go to the AWS Compute blog, find the 2019 pre-event, and you'll find all the deep links about this. So the first thing we did for streamed events is we basically solved what's called the poison pill problem. Now, the poison pill problem with streamed event sources is where you have a record in the stream that for some reason you just can't process. Maybe it's got a corrupted data format. Maybe it's gotten data from something that you just can't process. And so the way that it works with Kinesis and DynamoDB streams and SQS is we take that object in, or that message, goes into your Lambda function fails, and it goes back into that stream. With Kinesis, we basically continue to try and process it over and over and over again, where at some point we capture the number of failures that have happened for the same record. And in the past, what we would do is actually stop pulling records off of that stream. We'd basically break the event source so that you didn't lose any data. Now, for most of you, this was not what you wanted to have happen with your applications. And so what we've done now is give you a bunch of controls that allow you to do things like determine the max number of retries, to be able to do things like bisect a batch to smaller and smaller limits so that you can finally take that poison pill object or that poison pill event and discard it or send it to a destination. And so this gives you a lot more control over how you handle streamed events. We also, back in September, announced a capability called batch window, and this is actually more of a cost control. This allows you to say, only execute the Lambda function after you've collected a certain amount of data. So instead of pulling every second, maybe taking a record here, a record there, you say, no, I want to wait until I have many more events that I can process. It's a lot more efficient. And then we just 2 weeks ago announced a capability called parallelization factor. This actually allows you to take individual ordered bits out of a Kinesis shard and process it individually from the whole shard while still maintaining order. And so instead of you having to over-shard your stream, this again allows you to have a really high level of efficiency in processing records from Kinesis. For asynchronous events, we also just recently added a capability called max retry attempts. Now, previously, by default, and this was documented, we would retry asynchronous events twice. We launched this, and now you can either make it 0, 1, or leave it at 2 times that will do that retry for you before it'll become a failure. It was actually really funny. We launched this. We launched it with the exact same default that it had previously. We got an email from a customer who was furious. You've changed the retries. This is going to break everything that I'm doing. And we're like, no, this is actually how it's been the whole time. So if you thought for some reason that asynchronous was an idempotent request, go into this retry configuration, set it to 0, and that's going to give you what you thought that it was versus the 2 that it's always been. And then similarly with maximum event age, it allows you to expire out events that maybe have been sitting inside of a queue or a topic for a long time. Now, one other thing about this is another model that we have that we launched just this past summer with EventBridge, and it's the difference between directed and observable events. Now, with SNS and SQS and Kinesis, these are events that are basically going to be sent directly down to the consumed resource. You have very little filtering capability to stop that event from going there. But what we find is as organizations grow their distributed systems, you often want to have a message go to more than one place. But you might want to be really kind of controlling about how that happens. And so you might want an event that's more observable. Now, what we're all doing here is actually experiencing an observable event. I'm talking, some of you are listening, some of you are answering emails, or other things like that, but at the end of the day, the event is just being broadcast out. It's not me sitting one-on-one with you, saying things to you, and you nodding and definitely paying attention. And so when we look at distributed systems, this can be really, really powerful. For us at AWS, a lot of times we get a request for something. We obviously want to execute that request. We probably also want to log it. We possibly also want to send it into anomaly detection. We might want to also send it onto another system to put it into a database for BI or something like that. And so what EventBridge basically allows you to do is a really smart fan out across a number of services. We support a number of different destinations, including things like step functions. You can get really complicated workflows with this out. But beyond just being this kind of unidirectional fan out service, it's actually more of an omnidirectional channel. So this would allow any other service that is inside of your architecture to put a message into the bus, and then anyone can consume that message. And so there could be a lot of places where you might have complicated workflows where you have individual components that own some part of that workflow, and they could basically continue to share out their status to the services that care. Those can be consumed, and then they can move forward from there. Now, at Midnight Madness this week, we announced a new capability of EventBridge, which is called Schema Registry and Discovery. This is a really, really cool capability in this. Again, we see lots of customers that are building applications asynchronously. Those asynchronous events will have a certain JSON structure. And what you want is to take that JSON structure and have another team in your organization build something that consumes it. Now, typically, you would have to do this by saying, here's my JSON structure. What we find as teams get bigger and bigger, that requires then more communication, more overhead, more sharing of that. Instead, what you could do now in EventBridge is you can register a schema. It can also automatically detect these for you. Then those schemas are made visible and available inside of EventBridge. We take it one step further, though, with a capability called code bindings, which allows EventBridge to automatically generate for you code that could parse those events. We've integrated this with a bunch of IDEs. We've integrated this with SAM, our serverless application model tool. And so parsing events via EventBridge has just gotten even easier for you. Another capability that we have in terms of controlling the way that you handle events inside of your infrastructure is a capability called function concurrency controls. This allows you basically to set the bounds on how many execution environments for a given function can run. And basically, one of the key aspects about this is to help prevent a really aggressive workload that scales up very dramatically and quickly on Lambda from essentially DDoSing something downstream. So if you had a relational database, if you had another API you were talking to or third-party service, it would be pretty easy for a very heavy workload in Lambda to potentially overwhelm that. And so per-function concurrency controls give you the ability to, again, limit that to a certain amount of execution. Also has a really interesting capability to act as what we call a kill switch. So this can be really useful if you do have, say, downstream services that are broken, or maybe you take a maintenance window for something, and you want to make sure that stuff that is upstream that maybe is processing off of, say, a stream or a queue or an async service can be paused basically to not have to overwhelm that or to execute it and fail. And so per-function concurrency throttles can basically act as a point-in-time blocker to say, hey, stop executing, and then you remove it once you're ready to go again. Now, I talked about dead letter queues previously. Again, this is a capability that we've had in Lambda for quite some time. It's really useful when you have asynchronous workflows where there's the potential that you could have a failure, where Lambda would not be able to execute something, but you still want that event to stick around so you can maybe rerun it in another circumstance. Again, Lambda event destinations kind of supersedes this. If you are still using DL queues, don't stop, don't feel like you need to. But Lambda destinations is way more powerful and more capable than this was in the past. However, kind of across the board, if you're doing asynchronous workflows with Lambda, I really, really, really encourage you to enable either a dead letter queue or a destination for your failed events. If you don't have failed events, then it costs you nothing. If you have failed events, you'll be able to capture it, react, do something else. And so this can really help you with saving, again, events or data that get passed on to your functions. Okay, we'll talk a little bit about security. And I like to say, friends don't let friends do star policies on their IAM policies. We've seen over the last couple of years, a number of incidents where there have been security things that have happened. And one of the things that it comes back down to was over-permissive IAM policies. Now, with Lambda, there's basically two key ways that this plays in. We have what's called the function policy. So this is basically the policy that says, who can invoke this function? Is it Kinesis? Is it API Gateway? Is it S3? Is it another account? Is it a bunch of other accounts? These are all different things that might be able to invoke your Lambda function. We also then have the execution role. And this is what says, what can my Lambda function do with AWS credentials? Can it talk to S3? Can it talk to another AWS API? Can it read data from Dynamo? Can it put data in Dynamo? And so the execution role is the place where people typically end up putting those star policies where they shouldn't. And this is where you want to be really cautious about making sure that you're writing good IAM policies. Now, IAM, in terms of what it's capable of, a lot. Understanding IAM requires a PhD in Dead Sea Scrolls. It's really hard stuff to get to understand until you get a lot of experience with it. Now, I don't consider myself an expert in either IAM or Dead Sea Scrolls. I gave up the Dead Sea Scroll thing a couple of years ago, but primarily focus more on the IAM. And again, it requires a lot more time for you to figure out and to understand all the capabilities. Now, we have one thing that we've done, out of a number, but one thing in particular that will help make your life a lot easier. So we have a service or a tool that's called AWS SAM, Serverless Application Model. Some of you might be familiar with it. SAM is basically a template-driven service for launching, managing, updating serverless applications. And again, it's an extension built on top of CloudFormation, so it uses almost all the same capabilities. It can use a lot of the same syntax. However, we give you a number of special resources specific to serverless apps that greatly simplify the process. So this here is an example of a SAM template. It's about 20 lines of code. And what comes out of this is a Lambda function, an API gateway with an endpoint, a DynamoDB table, and then the IAM policies and glue that we need just to enable this application to work. Now, if you were to take these 20 lines and write it in raw CloudFormation, it would be about 100 lines of code that you would need to manage the same resources. So again, SAM by default greatly simplifies the work that you need to do. Now, buried somewhere in the middle of this code sample is a section that says policies. And in this case, the SAM example that we have has a policy that is called DynamoDB read policy, which has a single attribute, which is a table name. Now, as you might imagine, this is a policy that allows DynamoDB to be read for this one table. Now, this is something called a policy template, and what we've done with SAM is we've simplified over 50 different of the most common use cases that we have for serverless apps and created IAM policies for you on their behalf where we can dynamically pass in a reference object for them. So we saw previously an example for DynamoDB. I think I've got highlighted here an example for an SQS poller. And again, we've got over 50 of these today that cover a lot of the really common use cases that you're going to have with serverless apps. Now, I happen to think that SAM is a really awesome tool. We have the SAM CLI that allows you to do local debugging and testing and stuff like that. But many of you use other tools. You use Serverless Framework, you use Terraform, anything else that might be out there. So what's great about this file is it's basically an IAM cheat sheet. It's going to give you the exact policy capabilities that you need for these same use cases. If you don't want to use SAM, you can basically just drop that JSON into whatever tool you're using for deploying them and still get the benefits out of not having to dig through docs and figuring this out yourself. So I'd still encourage you to find this. You can find this in the policytemplates.json file in the serverless application model GitHub repo. Or again, you can follow that bit.ly link there. Okay. Whew. We just covered a whole bunch of stuff here in the execution environment. Again, we've covered everything from the fact that the memory knob also gives you more CPU, that turning that up may be more cost efficient and obviously a lot faster for your functions, that CPU-bound workloads look a lot differently than you might think. We talked about things like X-ray and how that can help you with profiling and troubleshooting. We talked a bit about how you want to think about event sources, right? You may feel that synchronous is way in to go, but if you think about asynchronous models, you could have a whole lot more efficiency in how you build distributed systems. We've got SQS, SNS, EventBridge, and Kinesis. Remember kind of the 6 ways that you can compare them. And again, I'll leave you with a follow-up exercise to dive into those so you can find out more about them. And then lastly, thinking about security and scoping down your IAM policies. Well, this isn't necessarily an optimization in performance. It's an optimization in security that you really, really, really want to think about. Awesome. So this brings us to our final topic, which is what you can do for being able to configure the Lambda service. So for a long time now, again, going back to talking about the lifecycle of a Lambda function, there's that point in time where we get that request where we don't have a resource for you. Again, we have to take a compute resource, align it to your account, we have to pull down your code, we have to bootstrap the environment, we have to execute your pre-handler code. All of that stuff before your function can actually get to the part where it executes your business logic. Now, we have for a couple of years had customers out there that would attempt to pre-warm a function. Typically, you would do this via some sort of cron-based call to another Lambda function or other code that would then go and execute Lambda functions. Now, this would initialize those environments, it would execute code, and it would get a pre-warmed execution environment available for you. However, it was really horribly inefficient. And actually, I would say that I worked with folks like our community hero, Jeremy Daly, about 2 years ago. He launched a package that makes this really easy, but it's still not really a perfect situation. For one, you're relying on hoping that we keep that idle execution environment around, which we give you no guarantee that it's going to happen. The second is when you do a pre-warming of a Lambda function, you're actually executing the function. So you're paying for that execution beyond the init, all the way up through the function handler. While you're doing that, you're actually blocking other requests from being able to use that execution environment. So even if you did every 5 or 10 or 15 minutes, say 100 parallel invocations of Lambda, you're actually blocking 100 requests from being processed for your workload. So just on Tuesday, we announced a new capability called provision concurrency for Lambda. Essentially, this replaces or removes that need for you to think about pre-warming. What provision concurrency does is it essentially gives you a knob to say, I want X number of worker environments available to process events. And what we do is we take that compute resource, we align it with your count, we pull down the code, we fire up that runtime, and we execute all the way up through your init. We don't execute the function handler. And so from that point forward, that function is now available and ready to take requests. This is going to give you basically a sub 100 millisecond little bit of overhead from the platform now compared to where it could be a lot more, there could be a lot more skew in it. So we see this diagram here from the launch blog that was done by Danilo, one of our technical evangelists, where if you look below the P95, so below the 95th percentile of performance, it's pretty consistent. But then when we go to P95, P98, P99, P100, what we see with the blue lines is that there was a lot of skew at the long tail of our performance. Then you see the orange boxes where with provision concurrency, that skew is really, really, really minimal. And that just becomes chalked up to some jitter that exists in the platform. So with provision concurrency, it does add one more basically one more cost aspect to Lambda. We do now charge you for the number of functions that you've provisioned in a 5-minute interval. But what we've done is taken the cost for compute duration, and we've reduced it pretty greatly. So if you use provision concurrency, and you use it at a pretty good utilization, typically above 75%, it's actually cheaper for you to use it than to use on-demand Lambda. So if you know that you're expecting a certain amount of concurrency, or you want to keep a certain percentage of functions highly available with low latency, again, this could end up saving you money. Now this is integrated with autoscaling, and so you can also use the same kind of autoscaling policies that you would to fluctuate this with over time, to be able to say, hey, I want to keep this at 110% of my concurrency over a sliding window, so it's always greater than the traffic that you have coming in. Or you could say keep it at 80%, so you're always guaranteeing a certain percentage, always hit this, always like lower available, highly consistent infrastructure. And so you've got all of those options there. And so that's provision concurrency. We think this is going to be a really huge change. So let me go back here. We think this is going to be a really huge benefit, especially for interactive applications, so those behind APIs, those that really have strong latency profile concerns. And so for some of you, that's going to matter. If you don't have that, you don't need provision concurrency. That's not going to be a benefit to you. So again, really think about what your need is for your performance profile. This should not be a default. This should not be for everything. Again, primarily just for synchronous and interactive workflows. Awesome. So we've covered a whole lot of stuff here today. We've talked about the 3 key areas that you can impact your performance of your Lambda functions. We've talked about your function code. We've talked about the execution environment, and then we've talked about the new provision concurrency capabilities that we have here that, again, we think are going to be a really big benefit to some number of you. Again, not for everyone, but again, not everyone ever needed to use the pre-warming methods in the past. So again, this is the picture if you want to grab it. This is your cheat sheet of all these things. I will not go through all these bullet points. We'll be here for another couple minutes. But with that, again, a bunch of different places, bunch of different knobs, bunch of different things you could tune. A lot of new stuff here in just the last couple weeks, including the last couple days. One last thing I'll mention is that we have a whole bunch of free training now out about serverless. So you can go to aws.training. You also go to aws.amazon.com/training and find out a lot more about this. Share this with your peers that aren't here in this room or back in your organizations and get them to ramp up and learn a lot more about this stuff. Again, my name is Chris Munns. I lead developer advocacy for serverless at AWS. You can find me at munns@amazon.com or come and bug me on Twitter at Chris Munns. Thank you very much.